Hey guys, my name is Michael, and I'm on Team 12808 RevAmped Robotics. This will be our third year competing in FTC, and when we look back on our rookie year, there were a lot of things that we wish we knew from the get-go when we were building our robot. Luckily for us, we had an experienced captain and coach to help get us up to speed, but we realized that not everyone has this kind of support. So in this video, we're going to go over the basics that you'll need for FTC from a mechanical standpoint, including basic building materials, robot components, mechanisms, a bit of robot design, and season planning. This video isn't going to be a deep dive that will tell you everything you'll ever need to know, but instead it's more of a broad overview of the things that you can use to build your robot, some of which you might not have thought about or heard about coming into FTC. Alright, let's start with a basic definition of an FTC robot. A complete FTC robot will usually have 4 main subsystems, and we'll take a closer look at each one later. First is a drivetrain, which you can think of as the chassis of the robot combined with motors and wheels. The drivetrain is what allows the robot to move and is also what everything on the robot is mounted to. We've got a picture of a Mecanum drivetrain in the top right of your screen. Next, we've got an intake system, which you can see in the picture below the drivetrain. Keep in mind that intakes can look really different, so the intake in this picture is by no means representative of what other intakes might look like. The purpose of an intake is to get the main game objective from the field into the robot. By main game objective, I'm talking about the objective that is scored primarily during the first 1 minute and 30 seconds of teleop. Some examples of main game objectives include the glyphs in Relic Recovery and the minerals in Rover Ruckus. Directly attached to the intake system is a deposition system, which is responsible for moving the objectives from the robot to the scoring location. Some examples of scoring locations are the CryptoBox in Relic Recovery and the lander in Rover Ruckus. Some teams might combine intake and deposition systems into one, but if you watch some matches, you'll notice that most robots have an intake action to move the objectives from the field to the robot, and then a deposition action to score those objectives. You can see an example of a deposition system in the picture left of the drivetrain picture. Finally, we've got an endgame system or mechanism. The point of this system is to accomplish an endgame objective that is unique every year. You might notice that I didn't include a picture of this mechanism, and that's because these tend to vary significantly from season to season. In Relic Recovery, the endgame objective was to put the relics onto the relic mats outside the field walls, and in Rover Ruckus, the endgame objective was to latch onto the lander. So that pretty much sums up your average Joe of an FTC robot. There are definitely exceptions to this 4 subsystem design, but for the most part, you'll see that most robots will have these subsystems in some form. In addition, on some robots, there may be small mechanisms that don't really fall under these subsystems. The jewel arms or knockers that many teams had during Relic Recovery are good examples of those. And who knows, maybe they might be necessary this season too. So now that you have a general idea of what a FTC robot is, let's talk about build systems. Build systems are basically sets of pre-made structural components such as C-channels that are made to be modular through the use of a hole pattern. These hole patterns provide mounting points for almost everything on your robot and enable fairly precise frames to be built fairly quickly. By being prefabricated, build system components save a ton of time. They allow you to focus more on designing your robot and less on executing your design. So what do I mean by that? Well, let's use Legos as an analogy here. So, let's suppose that you wanted to build a model out of Legos. Sounds pretty simple, right? Well, imagine how much more work that would be if you had to manufacture the Legos from scratch. You'd probably spend more time making the Legos than building the actual model itself. With build systems, it's a similar story, except the model is your robot and the Legos are the build system components. So, definitely use a build system. Not using one will put your team at a huge disadvantage. When it comes to choosing a build system, you've got a bunch of options, and we've listed just some of them on your screen. This year, we're trying Go Builda with a little bit of Matrix on the side. We've used Tetrix and Actobotics previously, so here's our 2 cents on these build systems. Tetrix is metric, and we really like their clean dimensions. The round numbers make it really easy to find dimensions without actually having to pull out a calculator. Actobotics is imperial, or inch-based, and has messy numbers on their dimensions, which makes it more annoying to create custom parts, but they make up for it by providing more mounting points and, as a result, more versatility than Tetrix. So finally, word on Matrix. So as I just said, we started using Matrix with Go Builder recently, and we found that the matrix channels are a little bit flimsier than those on other build systems. So we recommend that you probably don't use matrix on the higher stress areas of your robot. So again, this is our opinion. It's not really like fact-based or scientific, but it's what we think, and we just wanted to put that out there. Once you've chosen a build system, you're going to want to buy these components, and if you don't already have some, then the starter kit is a great way to go. Just know that if you buy one of them, it's not necessarily everything you're going to need, and you may need to procure more as the season progresses. Alright, so that's pretty much all we've got to say about build systems. Choosing a build system is pretty subjective, there's not like a single build system that's objectively better than the rest of them, so it really comes down to your preference, and the only way to find that out is by using a bunch of them, I guess. So the bottom line of build systems is it is much more important that you use a build system at all, and much less important which one you choose. Because build systems are mainly comprised of structural components, you're going to need some other parts to put an FTC robot together. So starting off this list, we've got machine screws. If you come from a woodworking background, then you may be more familiar with self-tapping screws, which, as you might know, sort of burrow themselves into the material. On an FTC robot, you're going to want machine screws, and these are screws with a very fine thread and a flat tip. They're not meant to penetrate the material, they're meant to go into a preformed thread in a part or a nut, and yeah, they're really important to have in FTC. We use them pretty much like every day. So yeah, you're going to want to have a bunch of these on hand. Some of the most common sizes that we might use are M3 and M4 if you're using metric, and number 6 if you're using imperial. When you're tightening something with the machine screw, you're oftentimes going to need a nut. In FTC, we like to use hex nuts because their hexagon shape enables them to be tightened easily with the wrench. There are 3 primary types of hex nuts. Plain old steel hex nuts, Keps nuts, which have little teeth on the back to help them grip into the material, and nylon lock nuts, which use a small piece of nylon on the inside to help the screw get a better grip and prevent it from loosening due to vibrations. When it comes to choosing hex nuts, we'd recommend that you only use nylon lock and Keps nuts, because the plain hex nuts tend to loosen easily under vibrations. You should use Keps nuts for prototyping and testing because they are easy to remove. Use nylon lock nuts for permanent installations or higher stress areas of your robot. While these are less convenient to remove, they will almost never loosen. Another useful component to have around are spacers. These are generally plastic, and they usually have a hole through the middle to allow a screw or an axle or something of that nature to go through them. These are used a lot, especially on drivetrains, to constrain motion. So if you want to have a wheel that only rotates and doesn't move side to side, then you could use spacers to constrain it on the axle so it doesn't move. Spacers can also be really useful when mounting electronics, and we'd really recommend that you have them around. We found that washers can also be very important to have around. You can see a picture of a washer in the center of your screen, and these are basically just thin metal discs with a hole through them for a screw, or sometimes the hole is also large enough for an axle. In FTC, we use washers to distribute the clamping force of a screw. This is especially important if you're going to screw something onto a piece of plastic or another fragile material. Washers can also serve as spacers in some scenarios, and we would recommend that you have washers of different sizes lying around ready for you. In FTC, we use bushings, axles, and shaft collars to facilitate rotary motion of all kinds. Axles are pretty much round metal sticks that sometimes have a flat side on them that makes them easier to grip. You'll find axles on FTC wheels, motors, and many other rolling elements. Shaft collars will help you keep axles where you need them. They're tightened around an axle, and their job is to prevent an axle from slipping all the way through a hole. Most axles and shafts in FTC are 1/4 inch or 6 millimeters, depending on what measurement system you're using and what build system you're using. Bushings are typically little tubes made of slippery material and are press-fitted into a hole where an axle will go. A little flange on the bushing helps prevent it from falling out of the other side of the hole. The bushing's purpose is to reduce friction when the axle is rotating. Linear motion is very common on robots and is one of the most popular ways to give a component linear motion. You simply just mount it to a linear slide. Some companies such as Rev offer kits that allow you to string aluminum slides into linear slides. These are very affordable but will bind or get caught from time to time, especially if the extrusion is warped. We've used these extrusion-based slides on previous robots and they get the job done. However, we also like to use telescoping slides. These use small metal balls to minimize the metal-to-metal contact and have a much smoother motion. We procure these from a website called Mizumi, where they're known as telescoping slide rails. However, you might also hear these types of rails called drawer slides. In order to drive either of these slides with rotary motion from a motor, you're going to need to string them using pulleys and a high-strength string such as fishing wire. We won't be covering exactly how to string a slide in this video, but there are plenty of in-depth guides on forums and YouTube that will show you how to do it step by step, and we'll try to remember to include a few of these links in order to transmit rotary motion. We like to use spur gears, sprockets and chains, or timing belts and pulleys. We use spur gears in areas where we only have space to keep the motor very close to the rotating component. Spur gears usually offer the best reliability because they're just two hunks of metal without anything between each other. However, usually keeping components and motors right next to each other isn't possible, and in those cases we use sprockets on the motors and components and use a chain to span the gap. The same thing can be done with timing belts and pulleys, but we tend to use sprockets and chains simply because we're more familiar with them. Keep in mind there are many different ways to transmit rotary motion. These three are simply the only ones that Let's recap. You'll want to have machine screws and nylon lock and caps hex nuts as fasteners. Use spacers to mount electronics and to prevent unwanted motion, especially on rotating components. Washers will be used primarily to distribute screw clamping forces. Axles, shaft collars, and bushings are essential to make many rotating components work. Linear slides usually exist as aluminum extrusion-based kits or telescoping ball-based variants. In order to drive linear slides, you'll want pulleys and a rotating component are close to each other, use spur gears. Otherwise, use sprockets and chains or timing belts and pulleys. There are a few basic components that we'd recommend you have, but probably aren't strictly necessary. Use these to augment your drivetrain or to build mechanisms with. Next, you might want different types of screws. Generally, you're going to want two types of heads and a variety of different sizes. So, you've got your standard socket head screws, but you also might want button heads. These also remove the necessity to have washers because the button heads help distribute the clamping force of a screw more evenly. The downside to these screws is that they are often made of a weaker grade of steel and also have a smaller drive, which makes them easier to strip. You might want to have more than just the most common sizes around because some mechanisms you build might need larger or smaller screws. In our mind, strings have two main uses. First is that they provide a tension force, which can be very useful for something such as a linear slide string. In addition, springs will provide a place to store potential energy, which allows the creation of many unique mechanisms. For example, we used a spring-loaded popper last year as our deposition system, and it allowed us to launch the game objectives into our sorting unit. Finally, ball bearings can also be very useful to have around. In some cases, you can use these instead of bushings to provide even lower friction for axles and other rotating components. Let's move on to consumables. Consumables are anything that will be used up and need to be replaced. These are really good for keeping organized. We usually use them for tying down cables and wires to make sure that nothing can get caught. However, we also think that zip ties can be great during prototyping, and if you are really desperate, sometimes you can use zip ties to attach components together. And so, yeah, zip ties are definitely really essential. Thread locker is also really useful to have. Thread locker is basically a compound that is meant to be put on a screw before it's inserted into the part, and once the screw is inside the part, the thread locker will cure and expand, which will lock that screw in place and prevent vibrations from loosening the screw. Thread locker isn't good for anything plastic, so that includes nylon lock nuts. However, it's very good for when you're screwing into a bare metal part, and thread locker will greatly improve the reliability of your robot, and it's just another way to prevent anything from going wrong. The brand of thread locker we like to use is called Loctite, and we use flexible silicone tubing, and we use it for two main purposes. First is making the noodles on our intakes, and don't worry, we'll get into what a noodle is. And also we use surgical tubing as a kind of spring for tensioning that we recommend you have, but definitely aren't strictly necessary. So first is gaffer's tape. This is kind of the best of both worlds of masking tape and duct tape. It's strong like duct tape, but doesn't leave a residue and tears easily like masking tape. At the same time though, it's not going to tear like accidentally, and so we found this to be super useful. The main downside is that it's a little more expensive than your typical duct tape lubricant. Is also really useful. We like the Super Lube brand, but really any brand will probably do. Sometimes on your robot you're going to want a slippery surface, or some moving components could benefit from an occasional lubrication. Also, these are really good for cutting and machining aluminum, which we do quite often. We create custom parts quite often. Whether it's because we can't find a part online or because it's too expensive, we've found it really useful to keep a supply of aluminum and plastic stock available with which to make these custom parts. For the uninitiated, stock is just another word for raw material. You'll also need wrenches. The purpose of wrenches are mostly to hold and tighten nuts, and we often use these along with hex keys to fasten things onto our robot. Some wrenches have a ratchet in them, which is very convenient, but they're often more expensive, and it's definitely not a feature. Hand tools you'll need to construct your FTC robot. First are hex keys. These are also known as Allen wrenches and are what you'll be using to loosen and tighten most of your screws. Not using the exact size for your screw could cause you to strip it, so make sure you get an assortment of both metric and dentistry and surgery, which is why on our team we call them dentist tools. Our main use for them is to hold or clamp things that are out of reach for us otherwise. Side cutters are great for making small and precise cuts. We typically use them around zip ties where we don't want to cause collateral damage to the stuff we've zip tied together, and they've worked out great for that, and are very sharp edges are generally pretty bad. You could cut yourself on them. Plus they're not allowed on your robot in FTC, so make sure to use a file to clean up those edges and deburr your parts. So there are some hand tools we recommend you have, but definitely aren't necessary to build an FTC robot. So first is a nut driver, and these are kind of like screwdrivers, but they fit nuts instead of screws. So these are really good for assembling the rev slides, the aluminum extrusion linear slides that I was talking about earlier. But generally, you're not going to be able to reach a nut with a nut driver simply because they're usually tucked away in a channel, and so these are situational, but when you can use them, they allow you to spin the nuts much faster than if you were using a wrench. Something else you might want to consider are a variety of different hex keys. Oftentimes these will have, instead of the little L thing at the end, they'll have a more comfortable handle instead, and if you don't really need that extra torque or something, these can be really useful and can be really a lot more comfortable to use over a long period of time. So if you've got extra budget or something like that are designed to shear sheet metal, and if you plan on working with aluminum or mild steel sheet metal, then seriously consider bench vices are like having a third hand, or at least that's what some people say. They're able to hold a part very tightly while you file, tap, or hand drill it. We don't use ours super often, but when we do, it's absolutely indispensable. Put a screw directly into a part instead of relying on a nut to clamp that part. This is where taps come in. After you drill a hole, you can then tap it to create threads. Some taps can be driven by hand with a tap wrench, but others are meant for use in a drill press or mill. When you're buying a tap, make sure to get the mechanism. The tension of the chain determines the reliability of the mechanism. You've got to get the tension just right. In order to achieve this correct tension, you're going to need to adjust the length of the chain, and to do that, you'll need to break the chain apart and put it back together after adding or subtracting some links. If you do this often, you should probably get a chain breaker because that will make the task a lot easier. Power tools are really useful in FTC because you'll be working quite often with metal. One of the most common things you'll need to do is to cut aluminum, and for that, you're going to need a saw. Generally, we recommend a vertical bandsaw because unlike a horizontal bandsaw or a chop saw, vertical bandsaw is capable of cutting curves, and chop saws and horizontal bandsaws are only able to cut straight lines. This can be really helpful because if you need a rough shape, you can just cut that out on a bandsaw, which can save a lot of time. Vertical bandsaws usually start at about $150, but can easily get much more expensive than that. In order to make custom parts or modify off-the-shelf parts, you'll need a way to drill holes. A hand drill could work if you're good with one, but if you want to drill perpendicular holes with decent positional accuracy and the ability to drill dozens of these holes at a time without getting tired, you're going to need a drill press. For FTC, a small one will work just fine, and on Amazon, an 8-inch drill press starts at about $100. Making custom parts can also involve bending sheets of metal or plastic. While you can bend metal with something such as a hand seamer, we think that you should still consider a small metal bending station, which will start at about $100. For plastic, it's a different story. Some thicker plastic sheets, like polycarbonate, will need to be heated in order to bend. For these materials, you'll probably need a bender designed specifically for plastic. In addition to these machines, you're going to need tooling, including assorted drill bits and spare bandsaw blades. These tools will all cost different amounts, but expect to spend at least $50 in total. So there are some machines that we recommend you have, but aren't necessary to build a solid FTC robot. So first of all, we got a belt sander, and the primary purpose of this is to remove sharp edges faster than a file. So if you have a file, don't worry, you're not really missing out on anything, but a belt sander is fast enough that you can sometimes use it to create a shape of a part, and that can be really useful. If you create many custom parts and you want very high accuracy on those parts, then you should consider looking into a mill, but it is very expensive, so just be aware of that. These will allow you to create parts that are accurate to within a few thousandths of an inch. If you're going to get one, we'd recommend that you get a DRO or digital readout. That will tell you the position of the machine, and so you don't have to do any mental math to figure stuff out. A scroll saw uses a small reciprocating blade to make cuts, and because this blade is so small, you can make some very intricate cuts with it. Something to note about the scroll saw is that you can actually start cutting in the center of a hole or a enclosed space by detaching and reattaching the blade, and that can be done pretty easily. On a scroll saw, you're going to have to use lubricant. This is important on all cutting tools really, but especially a scroll saw because the blade is so small. So yeah, overall, I don't find myself using a scroll saw too much, but you know, when the situation arises, there's not a whole lot that can replace a scroll saw for its functions. So we've got two main uses for our hand drill. The first is drilling holes, and the second is turning fasteners. We rarely find ourselves drilling with our hand drill, and that's not to say that a hand drill is necessarily bad at drilling holes, but we definitely like our drill press much more, and you know, if we can get a hole done on a drill press, then we're definitely going to do that as opposed to drilling on our hand drill. We tend to use hand drills for the second purpose much more often, and that's turning fasteners. A little caveat is that you want to turn the torque down on your drill beforehand, and you're going to finish the last little bit of tightening by hand so that you don't accidentally strip the screw, because it can be hard to feel how tight you're tightening the screw when you're using a hand drill. So Dremels have many uses, but we only use ours situationally, and generally that is to make a change on our robot without having to take a part off of it. If we want to edit a part while it's still on the robot, we can really easily go in with the Dremel and just cut a piece off instead of having to remove it, and that can save a lot of time, but usually we just rather get a cleaner cut with the bandsaw. So Dremels are definitely cool to have around, but definitely not necessary if you've got some of the other tools. A shop vacuum is very useful if you plan on doing a lot of cutting and grinding, because it'll help you clean up any of the small particulate matter or chips that end up on the floor and prevent them from getting into the air where people can breathe them in. So yeah, it's definitely not very important if you're just gonna assemble components, but if you plan on making your own, then definitely consider getting a shop vacuum. 3D printers are great at producing parts that require intricate geometries, but not a whole lot of strength. Examples would include phone holders and electronics mounts, but your imagination is the limit here. Also, while the machines can be expensive, they don't have to be. We purchase our FTC components from a few different websites. First is Servos. As the name suggests, they offer a large selection of hobby servos and accessories, and also this is where we purchase our Actobotics build system components. Next, RevAmped Robotics is a great place to purchase their expansion hubs, accessories, and Rev build system components. Pitsco makes both Tetrix build system components and Torqueado motors, and you can find all of those on their website. Next on the list, we've got AndyMark. They are primarily known for their Neverest series motors. However, they do make a wide variety of FTC components. Amazon needs little introduction and sells pretty much everything. However, we recommend that you purchase FTC specific components from the suppliers we mentioned above. McMaster-Carr stocks a huge variety of products, and you can begin your search at McMaster-Carr. They're kind of a one-stop shop for everything, but they usually have higher prices than other sellers. Mizumi is the website where we get our telescoping linear slides from, but they also sell a huge number of other engineering components that could be very helpful to you. By now you should hopefully know what you'll need for FTC and where to buy it. So we're going to start looking a little bit more closely at what you'll find on an average FTC robot. Drivetrains are arguably the most fundamental aspect of any robot. At their core, they're really just wheels that are somehow linked to motors, generally using the spur gears or sprockets and chains that we talked about earlier. Usually there's also a shroud that protects these exposed components, and the drivetrain also provides mounting points for everything else on the robot. There are 4 main types of drivetrains in FTC: Mecanum, tanks or 6-wheel, Omni, and Swerve drivetrains. Whichever drivetrain you choose, your robot's ability to move around on the field is critical. As a result, you're really going to want to spend enough time building your drivetrain and making sure it's solid. On a side note, we wouldn't recommend using AndyMark's wheels for building your drivetrain, mostly because in our experience they cause ESD, or electrostatic discharge. If your robot experiences an ESD during a match, you'll be a sitting duck for the rest of the game, and you'll probably lose that match unless you've already built up a sizable lead over your opponents, or your teammate is able to carry by outscoring your opponents in a 1v2 situation. ESD is definitely a very interesting topic, and we'll include a link to an article in the description below. Many teams have their own creative ways of preventing ESD, and this is ours. You're going to want to keep in mind that many successful teams do use AndyMark's wheels, and they haven't had any problems at all. In the end, we'd recommend you take this advice and any other ESD tricks a team might try to show you with a boulder-sized grain of salt. Definitely do your own testing and come to your own conclusions. Without further ado, let's move on to the various types of drivetrains and do a quick breakdown of each. Starting it off, we've got the Mecanum drivetrain. Before we get any further, let me briefly explain what a Mecanum wheel is. Take a look at the Mecanum wheel in the picture. Don't worry, it comes pre-assembled. Basically, a Mecanum wheel is lined with slanted rollers that can rotate freely. When it's spun, a Mecanum wheel produces forward and backwards forces like a normal wheel, but in addition to that, the Mecanum wheel creates lateral or side-to-side forces because of those angled rollers, and that's what makes these special. In a Mecanum drive, the wheels are oriented such that the rollers form either an X or an O shape. Then if some wheels are spun in opposite directions, either the forward and backwards forces or lateral forces will cancel each other out, and the robot will move only forwards and backwards or side to side. Because the secret sauce of a Mecanum drivetrain comes from the wheels themselves, a Mecanum drivetrain is extremely easy to build and requires virtually no maintenance. Because this drivetrain can change directions simply by switching the directions that it rotates its wheels, the speed with which a Mecanum drive can change course is limited only by how long it takes a motor to change its direction, which is usually a small fraction of a second. This makes Mecanum drivetrains the most maneuverable of all drivetrains. While the rollers give Mecanum drivetrains their unique benefits, they also cause the Mecanum drivetrain to have a few shortcomings. Because of how easily the rollers rotate, Mecanum drivetrains often don't have as much grip on the field as many other drivetrains. This opens the door for other robots to push yours around. While it usually doesn't matter, when defense is played, you'll be fighting an uphill battle if you're using a Mecanum drivetrain. The freely rotating nature of the rollers also results in decreased positioning accuracy during autonomous. This can be compensated for by running the autonomous and adjusting for any skid, but it's better not to have it in the first place. Overall, if you aren't sure what drivetrain to use, default to Mecanum. It is effective in most situations and extremely easy to build. Next, we've got the tank drivetrain. This is sometimes referred to as a 6-wheel drivetrain, but not all tank drivetrains have 6 wheels, although most do. You'll notice the picture we've included is a pre-built Andy Mark drivetrain. As I mentioned earlier, we would stay away from Andy Mark's wheels, but the chassis itself seems pretty solid. This picture is also a pretty good representation of what most of these types of drivetrains will look like. These drivetrains usually consist of 4 or 6 normal wheels and are probably what most people from outside of FTC would most easily recognize as a drivetrain. In 6-wheel varieties, some motors are chained to multiple wheels to help keep the motor count down. If you plan on going with this type of drivetrain, we'd recommend that you use 6 wheels instead of 4. Using 6 wheels will enable you to create a drop center drivetrain. In this kind of drivetrain, the center 2 wheels are positioned slightly lower to bear more load than their counterparts. This creates a pivot point at the center of your robot, which in turn helps it turn more smoothly. Another way to help this drivetrain turn more smoothly is to substitute the front 2 normal wheels with Omni wheels. If you don't know what an Omni wheel is, don't worry, we'll talk about those shortly. Like a Mecanum drivetrain, a tank drivetrain is also very easy to build and maintain. The difference between a Mecanum drivetrain and a tank drivetrain are that tank drivetrains utilize normal wheels. Because normal wheels have no rollers, your motors can hold your wheels in place and make skidding much less likely. This comes at the cost of maneuverability. A tank drivetrain is only able to drive forwards and backwards. If it wants to go sideways, it's going to have to turn towards that direction first. Tank drivetrains can be used to great effect by teams that are capable of playing a defensive driving strategy, but for most teams, a Mecanum drivetrain will likely be a better option. Next, we've got Omni drivetrains. These are named after their Omni wheels, which are basically just normal wheels that have rollers added perpendicularly to help them move in multiple directions. In order to make an Omni drivetrain work, you need to offset each wheel by 45 degrees, such that the wheels form an O shape. In practice, Omni drivetrains work very similarly to Mecanum drivetrains and share many of the same attributes. However, they have a few unique drawbacks that Mecanum drivetrains do not suffer from. So first, Omni wheels are slower than Mecanum wheels when going in all directions. Speed is something that usually has diminishing return in FTC simply because drivers can't use an excessive amount of speed. However, it's still something that is nice to have. Additionally, the angle of the wheels means that they require more space to be mounted than Mecanum wheels, and generally that space could have been used for something else. The angle on the wheels also makes it harder to climb objects, which is not always important in FTC, but a nice feature to have. The only thing that Omni wheels have over Mecanum wheels is the positioning accuracy in autonomous. Because the rollers are angled at 90 degrees, it's less likely to skid. So, can you see what we're getting at here? In our opinion, while Omni wheels can be very useful, we believe that the Omni wheel drivetrains are really just somewhat inferior versions of Mecanum drivetrains. Unless you have a very specific reason for going Omni, we recommend that you use a Mecanum drivetrain instead. Finally, we've got the Swerve drivetrain. This is probably the most unique among the four that we're talking about today, and is actually what we used last year. For the uninitiated, Swerve drives attach 4 standard wheels and the motors that drive them to individual pods, which are then turned by servos. You might be able to see the pods in the picture we've provided. The idea behind a Swerve drive is that by using normal wheels, we can get a good grip on the field, similar to a tank drive. But by physically rotating the wheels using servos, we can move side to side without having to turn the robot, and therefore maneuverability that approaches but can't quite match that of a Mecanum or Omni wheel setup. Also, a snake drive can be made that allows the robot to move in a curved line, and this can help compensate for the slow turning speed of the servos, enabling your Swerve drive to nearly match a Mecanum drive for maneuverability. So basically, the goal of a Swerve is pretty much to get the strengths of both tank drives and Mecanum wheels without the drawbacks, and in a perfectly executed Swerve drive, this is kind of the case. However, there's a reason that you don't see many Swerve drives. Building a Swerve drive well is very hard compared to other drivetrains, and programming one with a snake drive is an order of magnitude harder than programming a Mecanum or a tank drive. If we assume that you somehow build a perfect Swerve drive, it'll still take up much more space than most other drivetrains because the pods and motors need room to move. Also, you're going to have to spend 4 of your 12 servo motors on your drivetrain in addition to the DC motors that you're usually going to spend. In addition, the weight limit this year also means that a Swerve drive might be less than optimal because they tend to be heavier than other drivetrains. And this is not to mention that Swerve drives usually aren't designed or built perfectly, and this can cause a drivetrain to be extremely high maintenance and relatively unreliable. In fact, this was sort of the case for us last year, and well, it really sucked. Let me tell you, as the former driver for our team last year, a crappy Swerve drive sucks way more than an equally badly executed Mecanum drive, simply because there are so many more moving parts to mess up. So unless you absolutely must have the benefits of a Swerve drive, to the point where you're willing to deal with the high risk of failure, much higher time investment required, and various other drawbacks inherent to a Swerve design, seriously, please consider building another type of drivetrain. Alrighty, we're done with drivetrains. I don't think I have as much to say on the other mechanisms as drivetrains, but let's get started with intakes. So, as we discussed earlier, an intake is pretty much a mechanism responsible for bringing the objectives from the field into your robot. Then the intake will usually leave it for the deposition system to score the objective. However, sometimes the intake and deposition system are sort of mashed into one. In the world of FTC intakes, there are 2 main kinds of intakes: active and passive. As the name suggests, in an active intake, the driver has to actively operate the mechanism. This means that they have to devote some of their attention to the intake for most of the game. These intakes are also affected by operator error, which is quite likely to happen in most of your games. As a result, passive intakes tend to be much more popular and effective. In a passive intake, the driver turns the intake on and forgets about it. They can then just drive the robot into the objectives, and the intake should do the job for them. So passive intakes are usually superior to active intakes because they can't be affected by any operator error, and they are easier on the driver, which enables them to focus more on the game. Generally, if the game objective is small, you're going to want to use a noodle style intake, and if the game objectives are large, you're going to want to use a wheel style intake. We'll talk about both of those very shortly. Here are a few examples of active and passive intakes that we've designed, all of which I have used as an ARM driver for our first 2 or past 2 seasons, however you want to think about it. On the left, we've got an active claw intake from the Relic Recovery season. Claws and other active intakes have 2 main benefits. First, they can almost always double as a storage area, which can greatly simplify your deposition system. This might not mean much to you right now, but we'll get to deposition systems very soon, so just remember this. Next, they can be driven by a servo motor, which will save one of your valuable DC motors for other mechanisms on your robot. Unfortunately, active intakes usually suffer from a heavy performance penalty compared to a passive intake paired with a properly designed deposition system. The persistent issue in our claw was that it was difficult to operate because it required coordination between two people. In FTC, a robot's performance in the teleop period can be measured by its cycle time. We would define cycle time as the amount of time it takes for a robot to get the maximum number of objectives allowed by the game rules, score them, and then return to the objective pit or storage area. With our active claw intake, we found that cycle times were usually capped at around 30 to 45 seconds, which was okay for league meets, but definitely unacceptable for any tournaments beyond that. So a few months into the season, we completely rehauled our robot and mounted a passive wheel-based intake, which was a design that some other teams had already proven to be effective. The picture you see in the middle was one of our earlier designs, and even this was way better than our most polished active intake. Our designs and those of most other teams during this season used two DC motors which would power the left and right wheel, or wheels in the case of many teams, which would spin inwards and sort of suck the objective into a holding area. The goal with this design was to be able to intake objectives simply by driving into them. Obviously, this was much easier said than done, but we were able to construct an intake that met this goal. By making the intake itself do most of the work for collecting objectives, we were able to reduce the effect that operator error by myself or my base driver would have on our scoring ability. This is sort of the big idea of intake design, and that is to make the intake do as much of the work as possible so your drivers don't have to. In the end, we had a pretty successful season and made it to the elimination rounds in Houston. But before we move on, let's talk about where these wheel intakes are applicable. So a wheel-based intake has a few main attributes. First, it can be designed to work on objectives of almost any size and weight. However, wheel intakes take two precious DC motors to run, which is one more than the other popular passive intake. In addition, the wheels need to be spaced apart from each other to work. This spacing is based on the size of the objective. So, while you can decide what size objective you want to intake, whether 1 inch or 10 inches, you'll only be able to intake objectives maybe plus minus a quarter or possibly a half an inch of the size that you set, and that's stretching it a bit. So you can usually only intake one type of objective unless different objectives are the same width as each other. This would have been a problem last year because there were two differently sized objectives. One was a ball and the other was a cube. I'll also mention that wheel intakes usually don't work for round objects. So due to these drawbacks, you should only use wheel-based intakes when the objectives are large or relatively heavy. Both of these are kind of subjective, so I'll just say that anything more than 2 or 3 times more voluminous than a standard tennis or wiffle ball can be considered large. We'll consider something that weighs 2 ounces or more heavy. For reference, those snack-sized bags of chips that you might have are usually 1 ounce. Most of the objectives that FTC uses aren't heavy, although some are large. For small and light objectives, use a noodle intake. The picture on the right shows one, and the name comes from those yellow protrusions, which we like to build using a big fat zip tie with a length of surgical tubing stretched over it. In our opinion, the resulting noodle is stiff enough to transfer force while remaining flexible enough to give if there is too much resistance. It looks more like a French fry to me, but that's probably besides the point. These are attached to a central bar or axle, which is in turn spun by a DC motor. In this picture, a sprocket and chain mechanism is responsible for power transmission. When they are spun quickly, the noodles will sweep the objectives into your robot. Noodle intakes are the most common across most FTC challenges because they work well for the small wiffle balls and plastic cubes that are present in most FTC challenges. The picture of this intake was taken early last season, and we used something similar to it for pretty much the entire year. Obviously, we continuously adjusted and iterated upon it throughout the season, but the core concept remained the same. This year's objectives might be different from the standard balls and cubes, but I'm recording this before the kickoff, so we shall see. So you should have 2 main takeaways from this section about intakes. The first is that you should use a passive intake over an active intake whenever possible. The second is that your intake should do most of the work for your drivers. Your goal when it comes to designing intakes and any other part of the robot really is to make it as easy as possible to use. Okay, let's take a look at Deposition Systems. As I mentioned at the beginning of this video, these are designed to move your objectives from your robot to your scoring location. In FTC, most scoring locations require you to lift your objectives, so in order for a deposition system to accomplish its task, there will usually be a storage area for the objectives and an elevator to lift those objectives. Most of the time, the objectives will enter the storage area, and then the storage area with the objectives inside will be lifted by the elevator. However, if you look at the picture of our deposition system from last season, you'll notice that the way it operates is inconsistent with what I just said. Instead of entering the storage area and then being elevated, you might think that the objectives will enter the elevator first and then travel to the storage area, and you'd be right. In this design, our empty storage area would be lifted at the start of the game and left there. Then, once we gathered our objectives, they would immediately be launched into the storage area as we drove towards the scoring location. You actually can't see the elevator in this picture because it's a popper situated very low in the robot. Our popper worked like a spring-loaded catapult. A motor would stretch the springs down using a cam and add potential energy to the system. Then the springs would suddenly be released, and that would move a hammer and pop the objectives upwards rapidly. I won't get too in-depth on how this works, but if you're interested, tell us in the comments. If we find that there's enough interest in this topic, we might make a video on it in the future. Anyways, I mentioned earlier that an intake and deposition system can sometimes be rolled into one. Generally, in this setup, the intake doubles as a storage area, and all you need to have a complete deposition system is to add an elevator that can lift your intake/storage area. Hopefully, the benefit of an active intake almost always being able to double as a storage area makes a little bit more sense now. That's not to say that passive intakes can't become storage areas too. In fact, this is exactly what many teams did last year with their passive intakes. One of the fastest robots in Houston last year was by the team Boombots, and their design combined the intake and deposition systems. So why should or shouldn't you combine the intake and deposition systems? Well, the main reason is to cut down on time-consuming transitions. Moving your objectives from your intake to a dedicated storage area on a deposition system takes time, especially for a poorly paired intake and deposition system, which might take a long time to complete an unreliable transition. So, if we can use the intake as a storage area, then we don't have to spend time on a transition and there's no chance of failing that transition. So, why doesn't everyone do this? It's because an intake is heavy compared to a sheet metal or plastic box that doesn't have any motors, wheels, intake noodles, or other hardware on it. Having to move an entire intake up or down will cause your elevator to be very slow. If you instead use a light box with a small amount of hardware on it as a dedicated storage area, you can significantly reduce the load on your motor and allows your elevator to move your objectives much faster. If you're able to make your transitions extremely reliable and make your transition as short as possible, then you might be able to save time using this separate system design compared to combining the two systems and having a slower elevator. We'll put a link in the description to a video of a robot made by the team Gluten Free. In this video, you'll notice that they have two separate systems for intake and deposition, but their transition time is negligible. Their deposition system uses a super light box that seems mostly 3D printed. Because of this and their extremely light slide, there was very little load placed on their elevator motor, and combined with the way they strung their slide, they were able to run their elevator ridiculously fast. Much faster than they would be able to if they had put their intake on their elevator. When deciding whether to combine your intake and deposition systems, it really comes down to whether you want a transition and a fast elevator or no transition and a slower elevator. In any case, design your deposition system to be easy to use and be creative. Deposition systems should be built around your intake and the unique challenges that each season presents. A deposition system is often where your team can most easily differentiate its design from those of other teams. The last system I'll be talking about is the Endgame System. As I said in the beginning of the video, the Endgame System is designed solely to complete an objective that becomes available during the endgame period, which refers to the last 30 seconds of teleop. Because of how different the endgame objective is from season to season, endgame systems from one year are always, or almost always, dramatically different from the next. That being said, most endgame objectives require two things: linear motion, and a grabbing action. For example, in relic recovery, we had to grab a figurine called a relic using a claw and place it far outside the field. Most teams, including us, used a slide system to move the relic sideways and put it outside the field walls. So the grabbing action here occurred at the relic using a claw, and the linear motion was sideways and completed using a slide system. In Rover Ruckus, we used a latch mechanism that you can see in the picture to grab onto a handle. Then we used a lead screw to pull our robot up off the ground. Here the grabbing action was for a handle using a latch system, and the linear motion was vertical and done using a lead screw mechanism. Again, I'm recording this video prior to kickoff, but chances are the endgame mechanism will require your robot to grab something and move it in a line. I could be wrong, but that's what our team has gathered based on the challenges we've heard of and participated in. Linear motion is critical for a successful FTC robot, and if you didn't already know, you'll find that out very quickly as you build yours. In this part of the video, we'll be going over some of the most common types of linear motion in FTC, including slides, racks and pinions, feed screws, and slider crank mechanisms, as well as where each of these can be applied. In order for a motor to drive them, slides need to be strung. The way in which they are strung can affect how they work. We won't be going over how exactly to string a slide, but we will be putting useful resources for that in the description. There are two main types of slides in FTC, continuous and cascading. With a continuous slide, the stages extend sequentially, or one after the other. In a cascading linear slide, the stages extend all at once, or simultaneously. Theoretically, both slides will perform equally under the same load. However, in practice, this generally isn't the case. Relatively speaking, cascading slides can extend faster than continuous slides under very light loads, but for heavy loads, we'd recommend using continuous slides instead. Again, these are often made with aluminum extrusions or drawer slides, which our supplier calls telescoping linear rails. We personally exclusively use continuous slides because we have the most experience stringing these slides, and because our slides are usually put under a relatively heavy load that would require a continuous slide anyways. Whether you plan on using cascading or continuous linear slides, something you're going to want to consider is whether you want to use one or two sets of slides. In a slide system that uses just one set of slides, the mechanism will weigh much less and be able to extend and retract faster. However, the slide might sag or warp, especially at long or full extension, or with a heavier load. If your extension is especially long or your load is especially heavy, two sets of slides should be used. You will use two sets of slides, but only string and power one side. The unpowered side is only there for structural support. By building your slides this way, they will be more rigid and can support much more weight. The main drawbacks of a double slide are volume and weight. Because of the second slide, your mechanism will consume a lot more volume. That's because you need to leave a gap between each set of slides, so you'll lose that space in addition to the volume that the unpowered slides already take up. In addition, your extensions will be slightly slower due to significantly increased weight. Keep in mind that not only do the unpowered slides add extra weight, so do the pieces needed to connect the slide together. Generally, though, the speed decrease has a surprisingly small impact on real-world scoring performance. Overall, we'd recommend that you use slides when you need high-speed extensions and retractions, long extensions of 1 foot or more, and when you have a medium or light load. We wouldn't recommend using slides for removing a load of more than around 10 pounds. The main downsides to slides are that they usually take up a lot of space in a robot and are relatively high maintenance and time consuming to build and string. The next linear motion mechanism we're going to be talking about is the lead screw. In essence, a lead screw mechanism uses the rotation of a screw to cause a nut to move linearly. The load is usually attached to the nut and therefore moves with it. The two main variables to consider when selecting a lead screw are diameter and thread pitch. Selecting the proper diameter lead screw is important because a severely undersized lead screw is liable to break under load, while an overly large lead screw will add unnecessary weight to your robot. If you plan on holding up your entire robot with a lead screw mechanism, we'd recommend choosing a screw between the diameters of about 6 to 10 millimeters or 1/4 of an inch to 3/8 of an inch. Thread pitch is basically the distance between each individual thread on a screw. In a fine thread, the threads will be spaced very close together and the thread pitch will be small. On a coarse thread, the threads will be spaced far apart and the thread pitch will be relatively large. On imperial screws, the threads are usually measured in threads per inch, or TPI, while in metric screws, thread pitch is expressed as the number of millimeters between each thread. An example of an imperial notation would be quarter 20. This indicates that the diameter of the screw is 1/4 of an inch and there are 20 threads per inch. An example of a metric screw would be M6 by 1. This means that the diameter of the screw is 6 millimeters with 1 millimeter between each thread. You're going to base your thread pitch off of your load and speed requirements. A fine thread will allow you to move a heavier load, while a coarse thread will enable you to move the load faster. For a high load capacity, you're going to want to choose a high torque motor and have a high screw to motor gear ratio. For improved speed, you're going to want to select a low torque motor and a low screw to motor gear ratio. Because of how it works, a lead screw's extension range will correspond directly to the length of the mechanism overall. Depending on how well you design the mechanism, your range of extension will probably be at best an inch less than the length of your overall mechanism. So if you have a 14-inch mechanism, then probably the best extension range you're going to get out of it is around 13 inches. Knowing all this, let's discuss the selection criteria for a lead screw. Your desired range of extension should be less than 15 inches, and you shouldn't expect that extension to happen quickly. Finally, to justify using a lead screw, you should have a fairly heavy load. In this case, we consider heavy to be more than 15 pounds. Overall, you're unlikely to see lead screws very often in FTC simply because they're so slow. However, when you need to move something heavy, not many other mechanisms will do the trick. A rack and pinion is another popular linear motion device in FTC. Basically, a gear, which is called a pinion in this case, is mounted on a fixed servo. Then a toothed beam, which is called a rack in this case, is mounted on a movable component. Once the servo spins the pinion, the rack will move, and so will the component that it's attached to. Oftentimes in FTC, you'll see rack and pinion devices with two racks. The idea behind this is that when the pinion spins, there will be two moving components, and so you can design a more symmetrical mechanism this way. Basically, this means that you won't have to offset your device to account for lopsided motion. The range of extension of a rack and pinion is determined by the length of the rack, which is then determined by the length of the component. Because of this, racks and pinions can usually only extend a few inches at most. They're almost always powered by a servo, which keeps you from having to use a DC motor for a small extension. However, servos do have limitations. First of all, while they're surprisingly strong, most don't have as much torque as DC motors, so don't expect a rack and pinion to clamp an unsupported heavy object in place. Also, using servos means that the extension and retraction movements will be relatively slow, but because the extension range is so small, the extensions and retractions will still happen fairly quickly. So let's talk about where to apply racks and pinions. First, the range of extension you need will have to be within an inch or two, which can be doubled if you plan on having two racks. The speed of the mechanism is irrelevant due to the range of the extension, but just so you know, fully extending and retracting in a fraction of a second is probably good enough for most claw and clamp mechanisms. Finally, the clamping force provided by a rack and pinion usually won't be enough to counteract gravity for heavy objects, so make sure to provide those with extra support and use rack and pinions simply to hold the object still. You can see rack and pinions on some robots, and they're a really useful way to provide small movements to claws, gates, and other similar mechanisms. The final mechanism we'll be talking about is the slider crank. As you can see in the diagram, a slider crank has several parts, including a crank that is secured firmly to a driving shaft, such that when the driving shaft turns, the crank follows it. A rod connects the crank to the slider. The slider is the component that you want to move. It's important to note that unlike the connection between the crank and the driving shaft, the ones between the crank and the rod and the slider are hinges, which means that the rod can pivot from those 2 points. We find that a loosely tightened screw works really well as a hinge. When the driving shaft turns the crank, the rod is then pulled back and so drags the slider with it. Because the crank has a circular path, the slider will also move in a circular fashion unless you constrain it, and no matter what you do, the speed of the slider will always be sinusoidal. So a longer crank will give you greater extension range, but a shorter crank will give you greater force. Instead of using the stick that you see in the picture, we like to use a servo horn as our crank instead. A servo horn is usually a round disc that has a spline at the center for mounting your servo and a series of holes along the edge to mount components. This lets us choose where we want to mount our rod and lets us easily make our mechanism double-sided by putting in another slider and adding a rod on the hole opposite to the one we're currently using. With this setup, the length of the crank is the distance between the mounting holes and the driving shaft. Because the disc we use has its holes drilled in a circle, this can also be expressed as the PCR, or pitch circle radius. This is basically the radius of a circle that would pass through the center of all the holes. Similar to racks and pinions, slider crank mechanisms are driven with a servo, typically have short extensions because the crank has to be fairly short, and usually also have moderate clamping forces. Slider cranks and racks and pinions have similar applications and they can usually be used interchangeably. Compared to racks and pinions, slider cranks are usually more compact, so we tend to go with them over racks and pinions when we need short repetitive movements. Again, the penalties to using a slider crank are that they have somewhat circular motion and sinusoidal speed. However, we usually value the space we save over these small drawbacks. Let's talk about some of the ways we transmit rotary motion in FTC. There are 4 primary ways we do this, and they consist of direct drive, gears, sprockets and chains, as well as timing belts and pulleys. We'll be leaving out direct drive because that's simply when you plug the motor into the thing you want to drive, and it's pretty straightforward. So we'll just be talking about the other 3. We've got a picture of sprockets and chains in the top right, and a picture of gears in the bottom right. The timing belts and pulleys are to the left. There are a few reasons why we might use these in our mechanisms. The first would be to transmit or change the torque and speed generated by a motor. This enables the creation of mechanisms that require higher speed or higher torque than can be found in a typical off-the-shelf motor. The way you can express these changes in torque and speed are with gear ratios and gear reductions. Gear ratios are actually super simple, but they can seem confusing or intimidating if you aren't familiar with them. So here's a crash course on gear ratios. Keep in mind that these apply not just to gears, but anything with teeth. So that includes sprockets and timing pulleys as well. But for simplicity, I'll refer to all of these as gears in the explanation. Let's get some terminology straight first. The gear attached to a motor or rotation source is called the driving gear. The gear attached to your mechanism is called the driven gear. Pretty self-explanatory, right? For a gear ratio, the number of teeth is what's important. So as you know, on 2 meshing gears, turning one by a single tooth will turn the other by a single tooth. Knowing this, let's pretend that a gear connected to a motor has 48 teeth and the gear connected to the shaft of your mechanism has 24 teeth. In other words, the driving gear has 48 teeth and the driven gear has 24 teeth. The gear ratio is the ratio between the number of teeth in the driving gear and the number of teeth in the driven gear. In this case, that would be 48 to 24, which simplifies to 2 to 1. So, what does gear ratio mean? The gear ratio will tell you the factor by which your speed is multiplied. So in this case, your speed is doubled. But how do you find the factor by which your torque was changed? This is where gear reductions come in. The gear reduction is the reciprocal of the gear ratio, and is therefore the ratio between the number of teeth in the driven gear and the number of teeth in the driving gear. In this case, the ratio is 24 to 48, or 1 to 2, aka 1/2. So in this example, the gear ratio was 2 to 1, which tells us that our speed was doubled. Our gear reduction was 1 to 2, which means that our torque was halved. Seems legit. Let's do one more example. if the driving gear has 20 teeth and the driven gear has 100 teeth, what is the gear ratio and reduction, and how does the speed and torque change? This should be pretty quick. The gear ratio is 20 to 100, which simplifies to 1 to 5, and the gear reduction is 100 to 20, which simplifies to 5 to 1. This tells us that our speed is reduced by a factor of 5 and our torque is increased by a factor of 5. We'll link an article in the description in case you want more examples, illustrations, and explanations. Besides speed and torque change, another reason to use gears, sprockets and chains, or timing belts and pulleys is to get more flexible positioning for your motor. Using one of these transmission methods, you can flip your motor around, and as long as you make sure that the two gears, sprockets, or timing pulleys are coplanar, you can still drive your mechanism. In addition, you can change the proximity of your motor to your mechanism. This mostly applies to sprockets and chains or timing belts and pulleys because they have a chain or belt that you can easily adjust the length of, while gears have to be close enough to mesh. Even so, gears usually have a bit of flexibility in this regard, but it usually comes down to what kind of gear you're using, and we'll talk about that a bit later. Anyways, you can probably imagine how useful it would be to be able to put your motor anywhere in an imaginary circle around your mechanism. Compare this to directly driving a component where you can only have the motor in one orientation and you can only position it directly behind whatever you're driving. That isn't always a problem, but you'll find that if you direct drive everything, some of your motors will occupy precious real estate that you could probably use better for something else, which would force you to build your robot or design your robot based around your motor positions. By using one of the other ways to drive it, you can instead position and orient your motors based on how your robot is designed and put the motors in unused spaces instead. Let's finish this section off with a little summary on each kind of transmission. Let's start with gears. So these can be an extremely deep rabbit hole. There are many kinds of gears and many different variables that will affect how they work. Some of the few kinds of gears that I know of are spur gears, helical gears, worm gears, bevel and miter gears, as well as herringbone gears. Obviously there's way more. These are just a few that I know of. In FTC, you'll mostly see spur gears and the occasional bevel and worm gear. A spur gear is probably what you think of as a normal gear. Not much explaining to do here. A bevel gear, however, has its teeth cut at an angle. The picture on your screen should give you a general idea of what they look like. Usually, you'll want to use these when you want to mount your motor perpendicularly to your mechanism. Worm gears also allow you to mount your motor perpendicularly, but they probably shouldn't be used solely for that purpose because they always provide a fairly high gear reduction. So in other words, they're usually used to significantly increase your torque and reduce rotational speed. Only use worm gears if you really actually need this large gear reduction. By large, I'm talking at least 10 or 20 to 1, so a 10 or 20 fold increase in your torque. We've included a picture of worm gears. They look kind of weird. On the whole, gears are nearly as reliable as a direct drive mechanism and should be used when you have unused space next to your mechanism. So next we've got sprockets and chains, but I'm also going to include timing belts and pulleys because they both serve a similar purpose. So the main use case for these two is when you want to position your motor farther away from your mechanism. Generally, most mechanisms are driven by these because they have much better positioning flexibility compared to direct drive and gears. While they aren't as reliable as gears, they are pretty close, and when you tighten them correctly, they probably won't ever fail in your FTC season. We personally like to use sprockets and chains, but there are many teams that also have found success with timing belts and pulleys. Now that you have a better understanding of how rotary motion is transmitted in FTC, let's take a look at the motors responsible for generating it. Servos and DC motors provide all the rotary motion in an FTC robot. Generally, DC motors will have a round metal housing and a plastic cap on the end. This plastic cap is the encoder housing. In this context, an encoder is basically any device that can be used to keep track of something's angular position. When we're talking about motors, that something would obviously be the shaft. So because these motors have encoders, the name DC motor is actually something of a misnomer. These motors are in fact considered servo motors because they're able to keep track of their own position. But they're usually called DC motors, and so that's what we'll be rolling with. Encoders are extremely useful and important devices, especially in autonomous, because they can tell your robot where it is on the field, among other things. If you want to be a programmer, it's very important that you learn how to use the feedback provided by an encoder. There's actually a surprising amount to learn about encoders, both from a hardware and software perspective. So if you've got a bit of spare time, it definitely wouldn't hurt to do some research. Moving on, there are 4 main manufacturers of DC motors. The offerings from AndyMark go under the name Nevrest. Rev makes their Hex motors. Gobilda makes Yellow Jackets. And Tetrix makes Torquenados. That's a portmanteau on the word torque and tornado. We haven't really been able to notice a quality difference between any of these brands, so just pick whichever one you'd like. All of the motors will be able to spin clockwise and counterclockwise. They're also usually sold with gearboxes that provide varying gear reductions. Recall that gear reduction is an increase in torque and a decrease in speed. You do have the option to buy these motors without a gearbox, but they spin absurdly fast and provide almost no torque. So unless you already have something in mind, buy your motors with gearboxes. The 3 most common gear reductions in FTC are probably 20, 40, and 60 to 1. However, you can buy motors with gear reductions as low as 3.7 to 1 and as high as 188 to 1. Generally, 20 to 1 motors are used for applications where lower torque and higher speed is required, and gear reductions on the higher side, so around 60, are used for high torque, low speed applications. DC motors will come with one of 2 kinds of gearboxes, spur or planetary. As the name suggests, a spur gearbox uses large and small spur gears to change torque and speed. In a planetary gearbox, we've got a center gear called a sun gear, and in a planetary gearbox, we've got a central sun gear and several gears that rotate the sun gear, known as planet gears. The planet gears also mesh or make contact with a toothed track, which you can see in the picture. This is known as a ring gear. We won't be going over how they work, but planetary gearboxes are definitely pretty cool. So if you're interested, I'll provide a link in the description to a video that I think animates it pretty well. Because of how they're designed, planetary gearboxes do a pretty good job at distributing wear compared to spur gearboxes, and so they usually last a bit longer. Motors that come with planetary gearboxes are usually a bit more expensive than those that come with spur gearboxes, but we think it's worth it. Motors that come with planetary gearboxes are usually a bit more expensive than those with spur gearboxes, but we think it's worth it. However, prioritize getting a motor with the correct gear reduction for your needs over the kind of gearbox it has, because you usually have fewer options for gear reduction in planetary gearboxes, so it's quite likely that you might only be able to buy motors that come with spur gearboxes. If this is the case, don't worry about it. Spur gearboxes are still very durable under proper use. They're just a little easier to break if misused. The final gearbox consideration to make is the gear material. It's not super important, but be aware that the gears in a gearbox could be made of either a durable plastic called acetal or steel. Steel is obviously more durable, but acetal will work just fine as well. And by the way, that's Google's pronunciation, not mine. Alright, so when it comes to selecting motors, 3 things matter. First is gear reduction. A high gear reduction means high torque and low speed, while a low gear reduction means low torque and high speed. Next, there are spur and planetary gearboxes available. Planetary is preferable, but spur gearboxes are good as well. Finally, steel gears are usually more durable than ones made of acetal, but for the most part this doesn't have a huge impact on durability, so don't worry about it. Make sure to prioritize getting the correct gear reduction over the gearbox type and gear material. Here are some guidelines on when to use DC motors. You should make sure to check the game manual for how many motors you're allowed to use on your robot during your season. but that number has been 8 for a long time, so that's the number we're going to use. First off, you're almost certainly going to use 4 motors on your drivetrain, and so you'll only be left with 4 DC motors to use on the rest of your robot. Because of this, use them judiciously. So if an application doesn't need high speed or super high torque, use servos. Servos usually can't spin very fast, and some aren't even able to rotate continuously. But the torque they can generate is actually surprisingly high, so take advantage of that. So you should definitely use your DC motors fairly frugally, but make sure to use all of them. If you don't, you're almost certainly leaving a lot of scoring potential on the table. Alright, let's move on to servos. We've got a lot to talk about. So, servos are smaller than DC motors and much less powerful, but you're allowed to use more. For a long time now, this has been 12, but check your game manual just to be sure. As we discussed earlier, DC motors can also be considered servos due to their encoders. But when we talk about servos in FTC, we're referring to those little boxy ones. I said something similar in our section about DC motors, but servos are used for low speed and low to medium torque applications so that you can save your DC motors to do more demanding tasks. Directly out of the box, most servos are configured with a limited range of motion. If you need continuous rotation, most servos can also be configured for that. However, this isn't the case for every servo, and some might not even have their gear cut all the way around to save costs. You can see an example of that in the top picture, but the white plastic makes it sort of hard to see. Generally, this kind of stuff is rare, but know that it's out there, and if you can't get your servo to do continuous rotation, something like that might be why. For many applications of servos, you won't need continuous rotation, and in this case, a fixed rotation servo will work just fine. If you are using a fixed rotation servo for these applications, just make sure to turn the servo to one extreme of its range of motion before installing your mechanism at the corresponding extreme of its range of motion, so you can actually use all of a servo's range. The way you do this is with an external device called a servo tester, which you can use to turn a servo manually. With a servo tester, you can also easily diagnose whether a servo is working or not based on whether it moves and how easy it is to stop that movement with your hand. Servo testers built by one manufacturer are usually built for that manufacturer's brand of servos and can sometimes allow you to easily switch the motor between continuous and fixed rotation modes. My description of their abilities might not make them seem that helpful, but they're pretty much required to use servos to their full potential. So you're going to want to make sure you have a servo tester that's compatible with your brand of servos. There are a bunch of manufacturers of both servos and their testers, so we're not going to give you a list just because there are too many. Just in case you're curious, most of the servos we use are made by High-Tech and Rev, and we've included a picture of a servo from each of them. High-Tech has many models in their lineup, but Rev only has their Smart Servo, which is what's shown in the picture. We like the reliability of High-Tech servos, and they're available from Servo City, so they're easy to source. Rev's Smart Servos and their servo testers can be purchased off of their website. Whichever manufacturer you buy them from, servos come in a huge number of size categories from nano to giant, which are also called quarter scale. Usually we use larger servo motors because they have more torque, and every servo motor, no matter the size, counts as one servo, so we use quarter scales quite often. Servos all have gear trains, which are pretty similar to the gearboxes in DC motors, the only difference being that the gears in a gear train aren't in a special detachable box of their own. Because of that, if a gear train breaks, it's impractical to repair, and you can't simply buy a new one and slot it in, so you'll likely have to replace the entire servo. Because of this, many manufacturers will make their gears out of metal or special plastics and brag about their durability. You know, in the same way that Corning will brag about Gorilla Glass until you drop your phone and shatter the screen. I guess what I'm trying to tell you is not to trust the marketing material too much. For example, High-Tech uses a number of materials to make the gears for their gear trains. One is a proprietary plastic that they call carbonite. They also use steel and, in some of their high-end servos, titanium, which high-tech proudly writes in big letters on the sides of servos with these gears. Just before you pull out some fat stacks to go pay 180 bucks a piece for a servo with its gears made out of titanium, we're here to tell you that in this case, titanium is more marketing BS than performance enhancer. We would know. We actually bought and broke a bunch of these thingies this past season building our Swerve drive. Don't get us wrong. The servo itself is great, and there are reasons why it's so expensive, but I would hope at least that a titanium gear is not one of those reasons. By the way, if you want to go on ServoCity to see if I'm lying about the price, the model is HSB-9381TH. Titanium is a really cool material and has many great properties such as extreme corrosion resistance and a super high strength to weight ratio. The problem is that these gears don't make use of those properties. In fact, what if I told you that medium and high carbon steel can easily be made to be just as strong or even stronger than titanium? The only downside is that the steel is much heavier. However, in a tiny gear that's just a few millimeters in diameter, the weight savings are negligible, and you really don't need corrosion resistance in a sealed waterproof servo such as the HSB-9381. Okay, that was definitely a rant, but what you need to take away is this. Gear material is more important to servos than DC motors. However, most gears, even the plastic ones, will last long enough for you to make a mistake and somehow destroy the servo, in which case even a fancy titanium gear probably wouldn't save you. Or your servo, for that matter. In other words, operator error is very common and can easily break a servo no matter the gear material. While gear material can make a difference, it's not as important as some make it out to be. In order to control a servo, you need to send a PWM or pulse width modulation signal. But that's more on the programming side, so we won't talk about it too much. Just know that that's something you'll need to know as a programmer. A quick side note, if you plan on using the higher end high-tech servos, you might need to use a PAD or power absorption device, but not always. The main purpose of a PAD is to absorb any current that's sent back towards the controller device. So, final remarks. Servos are crucial to FTC robots, and they usually facilitate smaller motions in some mechanisms, and there are countless manufacturers and brands. They have fixed rotation out of the box, but they can be programmed or modified to be continuous depending on which servo you buy. Make sure to buy a servo tester that's compatible with your brand of servos, because they can do a bunch of useful stuff. Servos come in a bunch of different sizes themselves, and you'll probably end up using the larger ones because they usually have more torque and power overall. The gears can be made of different materials, but as I stressed already, this is not super important. Something that actually has a greater impact on the servo's life expectancy is how careful your teammates are when programming and installing them, or when using them while driving the robot. Figure out PWM signals if you plan on programming them, and finally, if you're going to use those crazy expensive high-tech servos, look into pads. You don't always need them, but you might. So again, use servos anywhere that you can so that your DC motors can be saved for more demanding applications. Let's briefly go over some of the sensors that you'll see in FTC. The first thing we've got is the gyroscope, and your phone actually has one of these. It's what enables it to figure out what orientation you've put it in and then flip the screen accordingly. Gyroscopes are used to sense angular motion, and in FTC we can use this to determine what direction our robot is pointed in autonomous, or how fast we're turning. Generally, gyroscopes are only used in autonomous because in teleop the drivers can manually control how fast and how much to turn the robot. Another sensor that sees a lot of use in autonomous is the distance sensor. These sensors are usually used to help the robot determine its proximity to the field walls. There are many distance sensors available, but ultrasonic ones are the most common. That's because they're cheap and accurate enough for most applications in FTC. Next, we've got encoders, and your motors already come with these, but you can buy standalone encoders for other purposes. Generally, these encoders are pretty precise, but make sure to check the manufacturer's spec sheet for more information. Wherever there's linear motion in your robot, there should be limit switches there to help prevent overextension and damage. Limit switches sense touch and can be placed at both ends of travel on a linear mechanism. You can then design your linear motion mechanism to touch one of the limit switches when it reaches the end of travel, and then disable the motor for that mechanism except in the opposite direction. Limit switches are super useful in teleop because when they're correctly installed, your drivers don't have to worry about damaging your robot, and they can focus more on the game. Light and color sensors are pretty self-explanatory, and their use cases are pretty niche as well. During seasons with objectives that are multiple colors, you can use light and color sensors during autonomous to tell your robot which ones it's picked up, or during teleop, if your drivers can't see very well into the robot, a light and color sensor can help them verify that they've picked up an objective. You probably won't see light and color sensors every year, but don't forget that they exist. The last sensor that you have is your phone camera, and this is actually an enormously powerful tool. Using computer vision or AI software such as OpenCV or TensorFlow, you can train your phone to look for something and essentially give your robot vision. Just make sure to keep these sensors and their capabilities in mind while designing your robot. Okay, we've gone over the primary systems in an FTC robot and over a bunch of stuff that you guys can use to build these systems. Now let's talk about some of the general guidelines and things to think about when you're designing any part of your robot. Obviously, the most important thing is time. You can't make changes unless you've got enough time to make them. So understanding that is key to a successful season. But what does it mean to have enough time? We usually answer this question by looking at how long we have until our next competition. In order for us to make a significant change, we need to have not only enough time to make that modification, but also to let our drivers get used to the modifications that we put on our robot. We'll give you a general roadmap of what your FTC season might look like, but because everyone's season will be different, make sure to be flexible. A good way to make sure you don't start making a change that you'll regret is to ask yourself if you have enough time at fairly regular intervals. Alright, so let's get started with the timeline. The game is released at kickoff, and you can start designing your robot for the game starting at this point. Make sure to carefully consider which direction you want to take your robot in before you start building, because it's only going to get harder to change directions once you've got something started. League Meet 0 rolls around in approximately a month and a half after kickoff, which usually turns out to be around mid or late October. Treat League 0 as a trial run, because that's what it is. It's just there to give you an idea of how future League Meets will be run. So for League 0, it's okay to show up with just an empty frame, but after that competition, you're going to want to know like a general idea of what kinds of systems you'll be building and how your robot is going to look by the end of the season. So by League Meet 1, you should have a drivetrain built so that you can at least score a few points by pushing objectives around on the field. Between Leagues Meets 1 and 2 and 2 and 3, build an intake and then a deposition system. It's fine if they're crude, but they should at least somewhat reflect your plans that you made at the end of League 0, unless you've got a good idea from somewhere else and you want to copy it. By the end of League Meet 3, your robot should be able to accomplish most of the tasks in the game, but it by no means has to do them well. A month after League Meet 3 is League Championships. This is probably the last window you'll have to make a major change to your robot. During this time, practice going through your judging routine and work on making sure that you've got at least a crude but working fourth system. By League Championships, you're going to want to have a robot that works to some extent because you've got to make it to Super Qualifiers to keep going in the season. Between League Championships and Super Qualifiers, work on fine-tuning your robot and your judging. Your judging is really important because that's the way that most teams end up advancing and is where most of the advancement slots are. Super Qualifiers isn't a super difficult competition to pass, but The competition starts heating up a bit at this point, and so your robot should be scoring, at about 75% of what you imagine your final design will look like. Hopefully, if you've been following along with this design progression and started practicing judging before league championships, you'll advance to the state championships. If you do, you should use the month that you're given to really put the finishing touches on your robot's major components and get your judging routine really nailed down. Make sure your drivers are used to driving your robot so that they can perform as well as possible. We can't really speak for your state, but FTC is pretty big in Oregon, and so we've got a lot of advancement slots, but we also have a huge number of teams that are competing for those advancement slots. After super qualifiers, if your robot has been performing less well than you've been hoping, you're really going to want to focus on your judging because that's the only other way to advance, and as I mentioned earlier, most advancement slots will come from judging awards. If you manage to make it to the World Championships, then congratulations, and make sure you don't make major changes to your robot during the month before Worlds, but repairs and small quality of life adjustments are usually okay. By this point, your team will probably be shifting focus away from working on your robot and more towards judging. At the same time, make sure your drivers continue to practice and really read through your judging script and make sure it doesn't reference things that are specific to your state, because the judges at Worlds might not understand what you're talking about. That is a general guide to this season, and depending on your state, this may or may not apply to you. Some states or regions may not have super qualifiers or league meets or some other competition, so find that out for your area. Again, make sure you always have enough time to do things. You don't want to get eliminated because your robot was partially down while you're making a change. We've gone over when you should have your designs ready over the course of the season, but how do you design? In other words, what are you looking for to help you decide how to design whatever you're making? Well, here are the things that we look for when we design the various parts on our robot. Realize that this criteria we've included works across seasons. In your season, there might be other specific things to keep in mind. Generally, you'll be designing around game elements, and so the elements we've listed will most likely be used in almost every season, so they're going to be the ones that we talk about. First up is the scoring location and its proximity to the objectives. Figure out the path you'll need to take to go between them. This will influence how you design your drivetrain and also might affect your intake and deposition systems because you might need to design them to help you move objectives towards your scoring location. Also consider how high you'll need to lift objectives to score them. This will obviously primarily affect your deposition system, which will need to incorporate an elevator. However, it could also affect your decision on whether to combine the intake and deposition systems. For example, if the extension is really long, I might choose not to combine the two because adding the additional load on the slide from the intake would be amplified by the extra length of extension. Moving on, we've also got to think about the objectives on the field and how they're arranged. This will usually affect your drivetrain design the most. Sometimes the field will be filled with obstacles and you'll need to weave around them, so you might want the maneuverability of a Mecanum drive. At the same time, a field filled with obstacles might also create a lot of choke points, which could make defense a more effective strategy, and for that you might want to go with a tank drive, or if you're feeling really frisky, a swerve drive in order to get that extra pushing power. Other times, an obstacle might surround objectives and force you to come up with a way to get over them or around them. Next, think about the primary objectives. Specifically, think of the size, shape, number of objectives on the field, and how many you're allowed to possess at one time. If there are multiple types of primary objectives, think of how their size and shape differ, if at all. Obviously, these factors will affect your deposition and intake systems the most because they need to literally fit these objectives, and so will be designed around the size and shape of the objective or objectives. The quantity of objectives and how many you're allowed to possess at once can nudge you to focus on various characteristics. If the quantity of objectives on the field is large, then teams that have the ability to score more are favored. Of course, even in this situation, having a reliable robot and consistent performance are still very important. If the quantity of objectives on the field is small, then teams will be rewarded even more for consistency and always being able to score the small amount of objectives that are provided. In this case, it's not nearly as important to be able to score a lot because the limiting factor is the number of objectives and not robot performance. Let's move on to the quantity of objectives that you're allowed to possess at once and what effect that has. If you can only hold a few objectives at once, then you're going to have to make a lot of cycles or trips back and forth between the scoring location and objective. If and when this is the case, make sure that your movements between the scoring location and objectives are as efficient as possible. On the other hand, if you're allowed to possess a lot of objectives at once, then efficient movement isn't as important. Instead, you're going to want to focus more on making objective collections and depositions as efficient as possible because these add up quickly when you're intaking or depositing a lot of objectives. A common but not universal feature of FTC challenges are that they have two sides of the field that play differently. We like to call these sides near and far, but the name isn't really important here. Sometimes one side of the field might be hard to score on, while another side might be easy to score on. And so this means that teams that played the easy side will be expected to score really fast, while teams that perform well on the side with more difficult conditions may not be as fast under the easy conditions, but might have some features on the robot that make them more effective at dealing with the difficult conditions. So, think to yourself if it's best to design your robot towards excelling on one side of the field and performing below average on the other, or if you would rather that your robot was decent at both sides of the field. So, in other words, would you rather be a jack of all trades or a master of one? Make sure to remember that in some FTC challenges, the game is equally difficult no matter which quadrant of the field you're placed in, and in this case, obviously, this rule doesn't really apply. Finally, make sure that your design conforms to the game rules. You'll need to work around many of these rules, but some of them can be exploited to your advantage. Hopefully, you now have a better idea on how to design your robot based on the game. In addition to making designs, you'll also need to know how to evaluate those designs to see if they're working or not. After all, in FTC, results matter. So first and foremost, we've got your scoring ability and consistency under competition conditions. Basically, you need to ask yourself how much you can score and how consistently you can attain that score while there are 3 other robots on the field pushing and shoving you and each other around. It's very important to mention competition conditions. Not only will you have more robots on the field, but your drivers will also be operating under louder and more hectic conditions than they're used to. Next up, we've got robot reliability. This is pretty self-explanatory, but it's hugely important. Reliability is the basis for scoring consistency, and in elimination rounds, most teams will likely pick a reliable robot with medium performance over a robot that has on average higher but more volatile performance. The final big category that we look at is our robot simplicity. A simple robot is often more reliable for 2 reasons. First, there's less to go wrong in the robot in the first place, and second of all, a simple robot is usually much easier to maintain, and as a result, you'll probably do it more often than if you had a complex robot that was a pain to service. Alright, that concludes our design section and the video, but wait, there's more. Stick around for some bonus tips on building your robot. If you've got questions on anything, feel free to leave them in the comment section or email us, and we'll do our best to answer them in a timely fashion. Also, if you feel like we missed something or our information was incorrect, be sure to tell us so that we can try to fix that mistake. It's our first time making this kind of video, so we'd love to hear what you think of it. Finally, if there's a specific topic you want us to make a video on, tell us. Your feedback means a lot to us, and I'm impressed that you made it this far in the video. Thanks for watching and have a great season. Without further ado, here's my teammate Sai with some helpful tips and tricks you can use for building your robot.
Hey guys, my name is Sai, and I'll be quickly talking about some tips and tricks you can follow to ensure a smoother season for you. Some of these things will be common tips, but many of these are things we've collected from our previous seasons and just wanted to share with you. Let's get started. Let's start simple. Make sure to always use nylon nuts. These use a nylon insert that keeps the screw in place. Also, make sure to use thread locker whenever inserting a screw into a threaded hole, but never ever in any circumstance use both of them together. Believe me, you don't want to find out what happens. Always keep safety glasses close at hand and be sure to wear them appropriately, such as when working with machines or Dremels or things like that. Thankfully, none of us learned this the hard way. When cutting thick metal, always be sure to use lubricant since it will 1. Reduce the amount of friction and time it takes to cut the metal, and 2. Prevent the metal from heating up too much since there's just less friction involved overall. A crucial thing you need to keep in mind is to make sure your parts are organized. Without organization, you'll be all over your shop, literally. As stated in the rules, you need to make sure to remove sharp edges and corners on your robot's components for safety. This can be done with the help of sand belts or files. Safety first! When working with wires, they can be very messy and confusing, so make sure to route them as cleanly as possible with the aids of tools like zip ties and tubes to keep them protected as well. Also, don't forget to label your wires. We had to replace an entire expansion hub at a competition, but we had labeled wires, so it made it much easier. Don't learn this the hard way. Always be sure to use button head screws or washers on plastic materials such as polycarbonate or acrylic. The increased surface area makes a big difference. And at competitions, make sure to run diagnostic tests on your robot to ensure functionality before going to a match. This is important because you can't really fix your robot once you've entered the field. But the most important takeaway from this all, have fun and stay safe. We'd like to thank you all so much. Whoever watched this video, it really means a lot to us. And once again, please feel free to contact us at revampedrobotics@gmail.com, it says it on the slide, or just drop a comment down in the comment section and we'll do our very best to reply to you as fast as we possibly can.